So in this short video, we're just going to look at creating a test model to represent a hospital medical gas or oxygen piping system serving a number of bed heads. Okay, so I may have a VIE system, so I'm just going to use a pressure boundary and I'll set the grid to isometric here just for convenience. So I'll just drop a pressure boundary there and I'll create my flow distribution pipework. So it's going to be copper or degreased copper in the medical gas system perhaps. So I'm going to branch upwards. Perhaps we're serving a number of stories in this hospital building, and I'll just come back down. Perhaps we have a riser, so I'm just including a number of vertical pipelines there, and I'm just going to assign the branch connection for the T-junction like so. Let me just stretch that a little bit, and I'll stretch it downwards as well like so. And now I'm going to include a number of flow outlets or flow boundaries to represent the 40 litres per minute flow of oxygen at each bed head. So again, I'll just copy those few nodes over to the left hand side like so. I'll just position them there, and I'll complete the connectivity with some additional copper piping. And you can see each component that I place in the flow sheet here brings with it some default information, which we can then very easily and quickly edit. Okay, so let me just tidy that up a little bit like so. There we go. So if I select any of these pipes, you can see by default it's 10 meters in length, it's 2 inch, and you've got your classification, your friction model, and so on. You can consider pipe roughness and scaling as well, and so on. Okay, but we're not going to look at that at the moment. This is just a quick demonstration. Just to tidy this up a little bit, I'm going to turn off some of the node identification numbers here, so it's just a bit more clear for us. I'll just try and center that a little bit. Okay, so we know the fluid is oxygen, so we access the fluid database and assign oxygen to the system. You can define the temperature, so let's just say it's 23 degrees. We'll just set the pressure at the inlet of this system to 511 kPa absolute, like so. And again, I want to edit the flow rate at each of these boundary flow nodes that I have assigned here into this model. So I'm just listing all of the components. So I'm listing all the pipes in the model like so, and now I'm going to list all the boundaries. So I'm holding the shift key and I'm selecting them all there, and we have 40 litres per minute coming out of each of these oxygen outlets. I'll make this linked pipe at the top 3 meters, and I'll just make these two connections at the bottom 1.5 meters in length. So perhaps we're passing pipework over a number of floors in this building, so let's just give the length of each of these vertical sections a length of 4 meters. And now I'm not giving any focus to sizing the actual pipes in the system as of yet. Okay, I just want to create the basic model connectivity and calculate to see what happens here. Okay, so we've got flow going through most of the system here, and we've got some warning messages. So we've got pipes highlighted in red here, we've got low velocities and flow in the critical region here, which basically means we're between the laminar and turbulent region. And if you look at the results, you can see then some of the calculated values for each of the pipes. Now we're showing the fluid phase as gas or vapor like so. You can edit or customize the visible properties. So I can for instance show the out fluid density and the out fluid phase state for each pipe, so you can see it's in gas or vapor phase and so on. Okay, now would be the time then to optimize your pipe diameters. Okay, so I mean, I just created this with default pipe diameters of 2 inch, which is 49.8 millimeter inside diameter. So we can look at, potentially reducing some of these line diameters. So for instance, I could list all copper pipes and highlight them like so using the shift key, and you can see they're all marked off here. And I can access the copper pipe database, or I can say, no, I don't want to use database values, and I want to directly define the inside pipe diameter. So I can do that like so and recalculate to refresh results once again. And you can see now some of the warning messages have disappeared, and we've still got some low velocities and flow regime in the critical region warning messages. Now, it's important to note that you don't have to eliminate these warning messages. They're there to prompt you into reviewing and evaluating the calculated values in the system. Okay, you can also turn some nodes off like so. So for instance, flow would be completely eliminated through that section of the system. Now, because this system is completely symmetrical, I don't actually have flow passing through this upper branch line, which is what we saw when I had calculated that model with these pipes turned on. So the software is clever enough to show you that I only need flow up to each of these lines, and like so, to the right hand side, to the first, second and third and fourth demand point, we've got flow, but then we don't have any flow passing through this point because it's completely symmetrical and we don't have a flow demand anywhere along this connection. So that's just a very brief overview on modeling a very simple test case oxygen piping system. And again, you can see I can show some result or input information on the flow sheet as well. That's just enough to get you started.